Okay, welcome back from spring break. This is lesson 14.1, types of numbers. Okay. Types of numbers, natural numbers. These are your counting numbers, and they start at 1, 2, 3, 4, no decimals, no negatives, and most importantly, no zero. Think of these as like numbers that would have been used in like caveman times when cavemen weren't concerned with things that didn't exist, and you can't count what doesn't exist. Okay? Whole numbers. Well, these are all the natural numbers plus 0. So 0, 1, 2, 3, 4, and so on. So the only difference between natural numbers and whole numbers is the 0. Next would be integers, and that would include the whole numbers that are positive and negative. So -2, -1 are like all the negative numbers that are whole, and all the positive numbers that are whole. No decimals, no fractions, nothing like that, just whole numbers. Rational numbers, okay, technically your book's definition and the word itself, the book definition is going to say any number that can be made into a fraction. And ratio is in the word rational. It means fraction. However, I think it's easier to think about it in terms of decimals. If you changed a fraction or a percent or a square root or whatever, any kind of number, if you changed it into a decimal and that decimal terminates or repeats, that's rational. Okay, repeating is rational, and decimals that terminate are rational. All fractions are rational, percents are rational, that kind of thing. Irrational would be the opposite, and your book is going to tell you numbers that can't be made into a fraction. Well, it's easier to think about it in the decimal form rather than the fraction form. An irrational number is a decimal that never ends but also never repeats. It's the never repeating part that's really important to remember. Okay, it sets it apart from the rational. Examples of this would be like pi. If your teacher has ever made you or asked you to memorize a certain number of digits of pi, it's hard to memorize because there's no pattern to it. There's no repeating. It's just seemingly random. And if you take the square root of a number like 10, that's not a perfect square, and you get a long decimal on your calculator, and that decimal technically goes on and on forever, and the digits of that are seemingly random. So they're long decimals that never repeat. Okay? Real numbers is basically all the types of numbers that we work with in algebra. An example of something that would be not real would be the square root of a negative number, like the square root of -4. As far as our class is concerned, we always say that would be no solution to that. But technically, there is a solution, but it's imaginary, and we just don't get into imaginary numbers until Algebra 2 Trig. So I'm going to do a little activity here where this is a Venn diagram. Venn diagram is just circles, and how they overlap shows their relationship. And this Venn diagram is kind of like a Matryoshka doll or a nesting doll, where the types of numbers all kind of fit into each other. For example, natural and counting numbers are the innermost category, okay? And then we have whole numbers, integers, rational numbers, and all of those are real, and irrational is its own little circle over here. Okay? So let's start with these, and we're going to take these numbers and we're going to categorize them. Okay? And right off the bat, I see here's a decimal. The ... means it goes on and on forever. However, it does not repeat. It's tricky because there's a pattern, 1 1, 2 2s, 3 3s, but that's not repeating. So it's a decimal, goes on forever, does not repeat. That's irrational. 2/5 is a fraction, and it's rational. It's not an integer because integers can't be fractions, but it is rational. 1.3 is rational. It's not an integer. It can't go any further into the circle. 1.3. Okay, let's skip around here. Let's go to 0. Okay, 0 is rational, but it's also an integer, and it's a whole number. So we're going to bring 0 all the way into that layer. Square root of 10, if I type that into the calculator, I get 3 point, a whole hot mess of decimal. So if that's a long decimal that does not repeat, that's irrational. Square root of 0.25 is 0.5. It's a square root, but it's a square root that has a decimal, terminating decimal answer. So technically, that's a rational number. However, since the answer is a decimal, we can't bring it into an inner layer. All right, -8 is rational, but it's also an integer. We can't make a whole number here. We can't bring it down to whole number because whole numbers can only be 0 or positive. -12/5 is rational. It's a fraction. 2 is rational. It's also an integer. It's also a whole number. And it's a natural or counting number. So we can bring that all the way into that layer. Let's see. 9.232323. You can see that they show the 23 3 times and then a ... When you see repeating values 3 times and then a ... that's another way of writing a repeating decimal. Repeating is rational. Okay. Pi. Pi is a decimal that goes on and on forever. That's irrational. That does not repeat. 2.6 repeating. Yes, it goes on and on forever, but it repeats, and repeating is rational. 4 is rational. It's also an integer. It's also a whole number. It's also a counting number. It can go all the way into that inner layer. Square root of 25 is 5. It's rational. 5 is an integer. 5 is a whole number, and 5 is a counting number. So, one thing I want you to get out of this is that square roots can fit many different places. It really depends on what the square root is. You have to type it in the calculator or do it in your head, like this is one you could do in your head, and see what the answer is to see where it would fit. Decimals and fractions that repeat or terminate go in this rational layer. Integers are any of these values and out. These irrationals are the square roots that don't come out even. It's a decimal you see that goes on and on forever, but no repeating, or pi. Okay, closure. The idea of closure is that if you're talking about a particular set of numbers that we just talked about, rational, natural, whole numbers, integers, whatever, we consider it closed under a particular operation like addition, subtraction, multiplication, and division, if and only if an operation between those numbers produces that same type of number all the time. Okay? If you can think of a counter example, which is an example that disproves that idea, then it's not closed. Okay, so let's look at this. Natural numbers are numbers like 1, 2, 3, 4. Okay? And under addition, it's closed. I can pick any two of these numbers on to a positive infinity, add them together. I'm always going to get a natural back. I can't get a decimal. I can't get a fraction. I can't get a negative. I can't get 0. There's no way to do that. Subtraction, though, is not closed. Like, I can think of an example of a natural number 3 minus another natural number 5, and the answer is -2, and that's not a natural number. So that's considered not closed because I have this counterexample. And there's many counterexamples, but all you need is one to prove that something is not closed. Multiplication is closed. Again, I can take any of these numbers and multiply them together. I'll never get a negative. I'll never get a decimal. I'll never get an irrational number. I'll only get natural numbers back. Division is not closed. I can take two natural numbers, divide them, and get a decimal. Whole numbers, almost the same as natural numbers. The only difference, remember, is whole numbers include 0, but that doesn't really affect our closure. Addition and multiplication are still closed. Subtraction and division still not closed because I can still make negatives, I can still make decimals. Integers, remember integers, we can include whole numbers now that are negative. All right, and in integers, the only operation that's not closed is division, because before we couldn't get negatives with wholes or natural numbers, but now with integers we're allowed to get negatives, so subtraction is now closed. But division is not, because we still can't have any decimals. And then when I did the notes, I accidentally put the integers chart twice, so my bad. All right, rational numbers, all of the operations are closed. If you add, subtract, multiply, or divide, you are, with a rational number, you're always going to get a rational number back. There are no counterexamples. Okay, irrational numbers. And I admitted this in class, and I admit it again, I messed up this chart. None of the operations are actually closed. Okay, addition is not closed because I didn't think about the example of whether when you added an irrational to its opposite. If you add opposites, that equals 0. And 0 is technically, it's not irrational. Okay? Also, subtraction. If I take pi and subtract pi, I get 0 also. So that makes it not closed. Okay? Multiplication is not closed and division is not closed, but these are the examples, or I offered similar examples in class. So it's the addition and subtraction that I messed up, and I apologize for that. And the set of real numbers is always closed for all operations. Okay, on your homework, we've got the vocab section here in the front, and you are absolutely expected to do your vocab section, look up your definitions in your glossary, and match them up to complete the sentences. Okay. For each list of numbers, determine whether they are included in the given set. So I would say if I was doing this set of homework, let's see. Let's do rational numbers. Let's do number 4. One strategy you could do is cross things out that you don't use. Like this is rational numbers. Okay. So 8. 8 is rational. I will use that as an answer. Negative 15 is rational. Fractions are rational. 0 is rational. Square root of 3. Uh-oh, if I put square root of 3 in my calculator, it's going to give me a long decimal that goes on forever. So I'm going to cross that one out. 9.5 is a terminating decimal. That's rational. Negative 4/5 is a fraction. That's rational. And 857 is rational. So I would just cross off ones that don't apply. Okay. If we go back here to number 3, 54 is an integer. Pi is not an integer. 2/3 is not an integer. Negative 16 is an integer. Remember, we're looking for only whole numbers. Square root of 2? Nope. 3.5? Nope. Fraction? Nope. And negative 594. The next section is asking you to tell whether a set is open or closed and under what operations, and they get kind of long with theirs. I'm going to say, like if we were doing number 8, integers. Okay, integers are closed under addition, multiplication, and subtraction. Okay, so that would be like one sentence. Then I would start another sentence that says integers are not closed under division. A counter example would be, and you can use the one right from your notes, to be honest. Okay, so if you're gonna answer this question, you get stuck, you can always go back to your notes, say we're doing integers, okay, close, 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 just write a sentence. Integers are closed under addition, multiplication, subtraction. And then the second sentence, they're not closed under division, and you just pull the example right out of your notes. Okay, 3 divided by 8 equals 0.375. 3 Okay, so they don't have to be as long as the example ones. In this section, I would highly encourage you to solve all these equations first. They're easy. You can do them in your head. X plus 4 equals 10. Well, 6 plus 4 equals 10. X squared equals 3. So X equals, you can leave it in radical form if you want, since that doesn't have a square root. Okay, hint, this one's irrational, right? Divide both sides by 12. Okay, X equals 0.25. So I would go through all of these and solve them all first. Then you can answer with the letters. So if you would go through all the ones, which ones are whole numbers. You would look at all the X values that you found, and if it's a whole number, then you would write that letter here. Like G would not count for number 14 because it's a decimal. Square root of 3, H, that's not a whole number, so I wouldn't put H here. So the first thing I would do would be to solve all these. You can do most of them in your head, and then you can categorize them and put them where they belong. Very important, we are not doing 19 through 28. You do not have to know how to do that for the regions. It's basically how do you change a repeating decimal back into a fraction, and you don't have to be able to do that for the regions. We're not going to spend time doing that. So just 1 through 18 is all you have to do. Thank you for watching, and have a great day.